Andrea, it's all yours.
Thank you very much, Jan, for this warm invitation. Also to Maria, who contacted me. And yeah, I'm really happy to take part to this European seminar about MR. And today I'll be talking about technical challenges and future direction of hyperpolarization. The talk will be focused on dissolution DNP. I mean, we know there are many techniques to produce hyperpolarization, but my field of expertise is dissolution DNP. I've been doing that for more than 10 years now. And I will be happy to share with you my thoughts and my research. So a little bit of background to start with, because we're all MR people and we know how great MRI is. It is unmatched concerning the quality of the contrast you can get, especially for soft tissues. Playing with the different relaxation time, you can enhance the signal of bones or lesions of muscles or fat, and this allows us to get really sharp images. And this is thanks to the abundant water, 33 molar in our body, that is the source of the signal we then transform into an image. But unfortunately, so there is nothing wrong with MR. So the question is, why do we need hyperpolarized MR? So unfortunately, some pathologies do not show fast enough morphological changes, because here with classic MRI, we image morphology. And for instance, one sad example is cancer. And I would like to drive your attention on how, for instance, cancer treatment monitoring is handled today. So in case someone is diagnosed with cancer, let's say if it's not too serious, you try to postpone the surgery and you try to solve the situation with drugs. So you go for neoadjuvant chemotherapy, for instance, and you go for a treatment that lasts 12 weeks, and then you image the tumor before the start of the treatment and after the end of the treatment, and you look for a recession. So you look for a shrinking in the size of the tumor. And this takes a lot of time, it's 12 weeks. And during these 12 weeks, the life of the patient is miserable, and this treatment costs a lot of money. And the last thing a medical doctor wants to say to a patient after 12 weeks of chemotherapy is, I'm sorry, this treatment didn't work. We have to restart from scratch. And on top of that, also, it's very expensive for the health system. So the question is, can we do that better? So can we assess if a treatment is working within days? So the answer is yes, but we have to change a little bit the paradigm. We can go back to the past, and Otto Warburg, Nobel laureate in 1931, he discovered a very interesting effect about cancer cells. So cancer cells behave a little different from healthy cells. So although there is oxygen present, they produce energy by aerobic glycolysis instead of oxidative phosphorylation. This is a process that, from the energetic point of view, is not very efficient. So cancer cells need a lot of nutrients to survive, and they produce a lot of lactate. So the consequence is that cancer cells have a very peculiar fingerprint. So compared to healthy tissues, they produce a lot of lactate, but we have to change the paradigm, because now we look at how an organ or part of it works and now how it looks. So we talk about metabolism. When we talk about metabolism, we talk about metabolites, small molecules that are mainly labeled in C13. And from the NMR point of view, this is a pretty good news, because the spectrum, the C13 spectrum, is less crowded than a proton one. So the chemical shift is more than 200 ppm compared to 14 ppm of proton. But there are two bad news. So compared to the water, metabolites are very diluted in our body, 10 millimolar compared to 33 molar that I showed before. And also the gyromagnetic ratio of carbon is 4 times smaller than proton. So at standard condition of an MRI scanner, the polarization is very small, and in turn, the NMR signal is very small as well. So we end up with a fingerprint of the metabolism of cancer cells that is very peculiar, but at the same time is very small. So the question is there a way to enhance this signal, so to improve the SNR and to be able to follow the metabolism of cancer cells in real time to assess a very accurate diagnosis of the pathology? The answer is yes. To do that, we have to fight a bit against the physics of the system. So we have to break the Boltzmann equilibrium and create a status that is called hyperpolarized. So with, let's say, a spin states with a very big difference between the energy levels. And this can be done. We can enhance the NMR signal by 4 orders of magnitude. And as I was saying before, we force somehow the difference between the ground state and the excited state to the maximum to enhance in turn the NMR signal. So there are many different techniques to do hyperpolarization. My expertise is dissolution dynamic nuclear polarization. So before getting to the dissolution step, DNP is a pretty old technique. It was known since the 50s. And what we focus on is DNP in the solid state at low temperature and moderately high magnetic field. So how it works? Let's consider an electron spin, so an ampere spin. And the big difference compared to the nuclei is that the magnetic energy associated to an electron spin is much higher, 1,000 times higher. So this means that at experimental conditions that are rather easy to achieve, so a temperature of 1 Kelvin and some Tesla of magnetic field, the electrons are completely polarized. If we then place a nuclear spin close enough to this electron that is coupled by the polar interaction, we can shine microwaves on this system, depolarize the electrons, and move this polarization to the nuclei. Therefore, we can hyperpolarize the nuclei, or if you prefer, we can artificially cool them down. So to perform dynamic nuclear polarization, then the first thing we need is an apparatus that allows us to create the experimental conditions to achieve this polarization transfer. So the key element is a polarizer. So a polarizer is no more than a magnet with a pole bore, because to prepare the electron spins for the polarization transfer, we need high polarization on the electron side. So we need magnetic field and low temperature. Then we have to prepare a sample in a very precise way. So we take a substrate we are interested in. So basically the metabolite we want to follow in real time. We mix it with some radicals. So the substrate is normally at molar concentration and radicals at millimolar concentration, a ratio of 1 to 1,000. And we embed everything in a glassing solvent. If you're interested to know why we need a glassing solvent, you can ask me questions later, because it gets a little bit more technical. Then, so we have this system that is dipole coupled. We start shining microwaves on the system, and if we connect an NMR spectrometer to the sample, we will see the NMR signal to slowly increase. And when we are happy about the polarization level, we can do what is called the dissolution step. So we inject in a controlled way hot buffer into the cold environment of the polarizer to suddenly melt the sample and extract a solution that is hyperpolarized. So this step is crucial because two things happen. So first of all, we dilute the sample. So we increase the distance between the electrons and the nuclei, because when the microwaves are not there anymore, the electrons are, so these paramagnetic entities or radicals, if you prefer, they are a source of relaxation, so they would destroy the polarization. And at the same time, we move from the solid state to the liquid state. And moving from the liquid state is very important because in the liquid state, all anisotropic interactions are averaged. And when we travel through low field, because here in the isocenter of the magnet, we have high field, and then the field decreases. So the liquid state is much more forgiving. So it's much easier to preserve the hyperpolarization in the solution. In this way, we get a T1, so relaxation time of our compound. It is a minute long, 2 minutes long, depending on what we are hyperpolarizing. And this allows us to then transfer the solution to a scanner, an MRI scanner close by, inject our patient or our animal, or just for in vitro experiment, and perform hyperpolarized metabolic imaging. So here I have a video that shows a typical preclinical dissolution DNP experiment. Is run, so this is my Danish lab in ADTU, is run on an Hypersense that was the first commercially available polarizer. As you can see, there is my colleague Magnus, was polarized in the solid state, and then the dissolution sticks goes into the polarizer, and Magnus gets this greenish solution, and the green comes from the color of the trityl. And this is just a polarization check. He injects the NMR tube into the resolution magnet, and you see a nice glucose signal on the screen that is decaying with a T1 that is approximately 30 seconds. So as you can imagine, the field is extremely multidisciplinary. You need physicists to study the mechanism, engineers to build the machines, then you need biochemists to answer the biological questions, and of course, clinicians, MDs, to take care of the patients. So depending on who you ask these questions, what does your ideal polarizer do, you will get a different answer. And I will try to cover 3 key questions in my opinion, at the moment. So it's, for instance, if you ask a physicist like me, especially at the beginning of my DNP journey, so what do you want from a polarizer? I would have answered, just, I don't care how much it costs, how long it takes, I just want unity polarization. Unity polarization is very easy to model, so we can progress on the theory, and the physicist is happy. If you ask the biochemist who wants to answer the biological question, well, for sure, she will answer, I would like reproducibility and high throughput. So the biological question is already so complicated that they want something extremely robust before injecting the hyperpolarized solution. And then if you ask the physician, so what do you want from a polarizer? It will answer, I don't want it there. So medical doctors, when you put complicated machine too close to their patients, they are extremely unhappy, although you paint them in white. So that's just to say they would like only the contrast agent. So if they could get the contrast agent without having the machine on site, as it happens for PET, for instance, they would be very happy. So I will try to cover these 3 questions, and I will start from the first one, the one asked to the physicist. So how to get then very high polarization. I have here a chronology of the polarizer built across the year. So the solution DNP was introduced to the MR community in 2003 by Jan-Erik, Andrea, and Larsen co-workers. And you see that everything started at this weird field of 3.35 Tesla. And the reason of that was because back then it was pretty easy to find microwave sources at 94 gigahertz that could output a decent power. Then Oxford, from the patent of written in Malmo, Oxford built the first commercially available polarizer, the Hypersense, in 2006, again 3.35 Tesla, so no improvement for what concerns the field, but they just added some automation on it. Then GE was holding all the patents, developed the first 5 Tesla polarizer. Then we did a lot of development until 2013 in Lausanne. We built the first 7 Tesla polarizer. And then Jan-Erik in Denmark, after he opened his lab, the Hypermag, he investigated the polarization up to 10 Tesla. So as you can see, the field increased across the year. And why is that? So why do we have this quest for high field? Well, if you put on a graph, basically the pyruvic acid plus trityl data collect a different magnetic field, you can see that the polarization follows this law, is proportional to the magnetic field over the temperature. So increasing the magnetic field eventually will yield higher polarization, and all these graphs taken from the literature, they follow pretty well this increase, this law. But then why not 10, 20 Tesla? Well, there is a limitation. So at some point, this trend saturates, because this law here is valid until the nucleus you're polarizing. So in our case, most of the time is carbon. So the Larmor frequency of the carbon is smaller than the width of the spectrum of the radical. So basically, the nuclei where we are hyperpolarizing frequency-wise, they have to fall inside the spectrum of the radical we are using in this case trityl. So when you go too high in field, this law here, this condition here is broken, and your polarization transfer is not efficient anymore, and this trend saturates. So 6.7 Tesla seems 6.77 Tesla seems to be the sweet spot. Something very interesting happens for pyruvic acid and trityl at 6.7 Tesla. Basically, just mixing pyruvic acid and trityl is a perfect sample. Because across the year in the literature is well known that you can tweak the polarization, increase it even further by adding gadolinium, that is a T1E, so shortening for the radical, so it reduces the relaxation time of the radicals, or you can apply microwave frequency modulation. That is irradiating your sample with non-monochromatic irradiation of the microwave. So you basically change slightly the frequency left and right to cover a broader portion of the spectrum. So let's try to understand why at 6.7 Tesla, it just works, pyruvic acid and trityl, and there is no benefit from neither gadolinium doping nor frequency microwave modulation. So the T1E decreases linearly with the field. I found these 3 nice dots in the literature. So if the T1 of trityl at 3.35 Tesla is around 1 second, then it decreases to 600 milliseconds at 5 Tesla and 300 milliseconds at 6.7 Tesla. And the problem is that when the T1E is too long, let's say the electron turnover is not efficient enough, so other relaxation processes can kick in, and your system is not optimal. So you are building polarization, but you're losing polarization for other reasons that are not involved with the radical, and so your maximum achievable polarization is lower than it could be. That was the reason why at lower field, so when the field started at 3.35 Tesla, many researchers started adding gadolinium, so to shorten the T1 of trityl. At the same time, for trityl and pyruvic acid at 6.7 Tesla, is micromodulation does nothing. And the reason is that so trityl is narrow enough and the electrons are so tightly bound that the saturation of the SR line is very efficient. So you can see here, so this is the T1E of the trityl in pyruvic acid at 6.7 Tesla, 300 milliseconds. And this is how fast you can saturate when you switch on the microwave. So you can see how faster is the saturation with respect to the T1E. And this means the consequence is that micromodulation doesn't add anything. But this is a special case. This is a special case of pyruvic acid and trityl. So what happens to other formulation? For instance, to UV radicals, that is my favorite topic. So these radicals are a little bit different. They show much shorter T1. So the T1 is between 5 and 10 times shorter than trityl. And if you do DNP at 6.7 Tesla with monochromatic irradiation, you see that the enhancement is pretty bad. So you don't get more than, for instance, 10% polarization on carbon. This was a glucose sample, for instance. And the reason is here. So you can see that the T1E is much shorter, and at the same time, the saturation is slow. So these are inefficient conditions for DNP. Different if you start modulating, so if you start brushing wider on your ESR spectrum, everything becomes faster on the from the saturation point of view, until when you follow here, so below the T1E curve, and suddenly the enhancement is boosted by 3 to 5 times. So also with an expensive radicals like these UV-induced radicals on commercially available molecules, if you use your tools carefully, you can achieve very high polarization, so 50% polarization on carbon with a build-up time that is relatively short. Differently, trityl in other matrices, so in other solvents than pyruvic acid, for instance, glycerol water, that is a widely used solution to dissolve other molecules that are not pyruvic acid, for instance, glucose, acetate, alanine. So the T1E, although the concentration of radical doesn't change with respect to pyruvic acid, and the field is the same, the temperature is the same, the T1E of trityl in glycerol water is much longer, is 1 second at 6.7 Tesla. And this is inefficient from the DNP point of view, because the turnover is not fast enough. So in this case, you can add gadolinium, although you are at high field already, until when basically you match what we call the pyruvic acid condition. Because when you add gadolinium, two things happen. The T1E of the trityl gets shorter, and also the spectrum becomes narrower. And narrower means more electrons focus to transfer polarization only to carbon-13. So you can see here that the ESR spectrum of the trityl gets narrower when we add gadolinium, and so does the DNP sweep. So, and you see that, so for this sample, for instance, the optimum was found around 1 millimolar of gadolinium. And you see that 1 millimolar brings the T1E very close to the one of trityl and pyruvic acid, and also the width of the spectrum. And in this case, basically you match with 1 millimolar of gadolinium in glycerol water for glucose polarization. You basically match the polarization, this fantastic 70% you can get on pyruvic acid without gadolinium. So long T1E, short T1E depends on the sample. One common feature when you go towards higher field is that everything becomes slower from the nuclear point of view. So polarizing your substrate takes more time. And the polarization time increases with the square of the magnetic field. So it can become very slow. So if a sample took 20 minutes to polarize, 30 minutes to polarize at 3.35 Tesla, it can take 2-3 hours at 6.7 Tesla. So the price to pay for higher polarization yielded by higher field is a lower throughput. So the second question is about how to make the biochemist happy and increase the throughput and the reproducibility of your hyperpolarization. So there are two main approaches. So we can go faster on the single sample, and to do that, we can use what is known as cross-polarization. It is an approach that Professor Sami Janin has investigated a lot during the last 10, 15 years. Basically, what you do is you use a radical that is optimized to polarize protons, so the protons in your sample, because the protons are abundant, spin diffusion is fast, the polarization is much faster, and then you cross-polarize, so you have a double coil, you match the Hartmann condition, and you transfer polarization from the protons that are fastly polarized to the carbon. It's an interesting approach because everything can go up to 5 times faster. So radical as tempo are inexpensive compared to trityl, and readily available on any basically retailer of chemicals like Sigma Aldrich of Cambridge Isotopes, if you prefer. And it is also useful to polarize, let's say, unusual DNP samples. So to use sort of scaffolds, porous media with radicals grafted inside, because you can polarize the protons of this porous media, and then spin diffusion will transfer it to the DNP juice, so to the solvent, and then you cross-polarize the current. But there are also drawbacks, because it works only for small samples, because to match the Hartmann condition between proton and carbon, you need really high B1 in the NMR coil. And of course, the smaller the sample size, the easier it is. The polarization relies on the efficiency of your NMR system. So it's not only about shining microwaves, you need performant NMR. And if at some point your NMR is not working anymore because your circuit broke, you cannot hyperpolarize anymore. And also, let's say with introduction of cryogen-free polarizer, so magnets, polarizer that do not get liquid helium from an external dewar, but they have a cryocooler, a cold head that liquefies the helium gas. Let's say the bottleneck is not exactly the polarization, because is the sample turnover. So if being the cooling power of this cryogen-free polarizer limited, you cannot load and unload samples fast at will, so to say. So you have to let the system to thermalize properly. So another approach is to go multi-sample, so to polarize more samples at once, and let's say use all the available sample space in the polarizer. To do that, you have to rethink a little bit how you load the sample in your polarizer, because, for instance, it is not very practical if you use something, let's say a sample holder that is rigid, as in the video I showed before, where we have basically a stick that brings the sample from outside into the sample space, and another stick that is coaxial and brings the hot solvent to perform this solution. So you have to rethink a bit your system. You can move to something that we call a custom fluid path. It's a flexible sample holder. It is at the same time sample holder and the dissolution system. So we developed our own. It's pretty robust. It's the same system basically that Kiel has on the spinal liner. It is reusable and easy to use, because it comes with a screw sample cup, and the leak tightness is made compressing a Teflon O-ring here. The dissolution buffer comes separately, so you don't, for instance, as on the spin lab, where this fluid path is pretty bulky and you have to load it together with the dissolution buff. So it's very versatile. It's robust. There are no glue joints. Everything is, there are mechanical tight fits plus a laser welding here. So it's very durable. Kiel witnessed more than 100 dissolution with the same fluid path. We were very happy about that. And it is also pretty easy to implement. So we, let's say, beside the spinal liner, we also implemented fluid paths on custom-made polarizers in Paris, in Vienna, in Cambridge, in Lund, etc. I think there are now 7 or 8 labs using this dissolution technology now, separated from labs with a spinal liner. And when your sample cup is flexible, you can really, so everything gets easier. So I have a video here of my PhD student at the time who is loading a fluid path in, let's call it a horrible dissolution DNP polarizer, because it's extremely tall and extremely long. And the dissolution is extremely easy. So you have, so the sample is polarized, TAN just connects the fluid path to the dissolution buffer, and he can run the experiment on his own, and there is no repressurization of the cryostat and no hot sticks getting into helium, etc. Everything is simpler and safer. And when you're when you have a sample holder that is flexible, you can think about more advanced design of a DNP probe. For instance, we designed this one that can polarize 3 samples at once. This was part of TAN PhD thesis, and we also implement parallel detection. So we have 3 different coils. We can follow 3 samples at once with a 3-channel spectrometer. You can see that the sensitivity is very similar on the 3 samples, and we were able to perform 1 dissolution every 15 minutes, with the heating of the buffer being the bottleneck, not the turnover of the sample in the core. Now I come to my favorite topic, that is how to make the physician happy. So how to get rid of the polarizer on site. So in the introduction, I talked about the solution step. That is something crucial to shelter the polarization as far as we use traditional samples. So as far as we use radicals that are persistent. And the reason is that if we try to hyperpolarize something and extract the sample as a solid to be stored at appropriate condition of field and temperature to then travel further away, so to a distance that requires more than the liquid state 1 minute time, and we perform a dissolution on site, unfortunately what we get is noise. So with standard sample, this procedure would not survive. And the reason is that the same interaction that we use to create the hyperpolarization upon microwave irradiation, when we try to extract a sample in the solid state and we travel from the isocenter here to the stray field of the magnet, it is few tens of millitesla. Basically, this interaction plays against us. It's a very efficient solid state relaxation at low field is extremely fast. So it goes with the square of the magnetic field. So at very low field, in few milliseconds, we will lose all the polarization we built in the first place. So a solution is to use radicals that are non-persistent. So radicals that are there when we need them, when we want to transfer polarization from the electrons to the nuclei, and are not there when we want to extract the samples and as a solid to be stored and travel far away. So during my PhD, I started investigating this family of molecules that are called alpha keto acids. So the common feature is this decatone group here, and then you change the functional group here that will affect the appearance of the ESR spectrum. So if you freeze these molecules instead of the radical in a sample that contains, so then these radical precursors, as I will call them, mixed with some glassing agent, water glycerol is fine, and the molecule of interest, be pyruvate, acetate, glucose, etc. So you freeze them in liquid nitrogen, you shine pretty strong UV light, and in few minutes, 2-3 minutes, you generate enough radical to perform efficient DNP. So we are in the tens of millimolar radical. This is enough to perform efficient DNP at even at high field, as I showed before, just by using microwave modulation. But most importantly, these radicals are stable below 200 Kelvin. But above 200 Kelvin, they recombine in the magnetic species. So since the quenching of these radicals happens before melting the sample, we can think about polarizing the samples and then heat up the samples to this level here to then freeze the polarization in the solid state and have a solid sample that is hyperpolarized but radical free. Basically, we get rid of, with this heating of the sample, we get rid of the interaction that was bothering us when we want to try to extract a sample in the solid state. Across the years, we published a number of papers that explain how to produce this sample from and how to polarize them efficiently from A to Z. Okay, so how to use them? The first part, so the polarization, is as usual. You treat it as a normal DNP sample. You produce the sample, you put it into the polarizer, you shine microwaves. The T1 of this radical is pretty short, so you need microwave modulation. In this way, we can reach pretty high polarization. So this was a glucose sample, so 40–50% polarization after 1.5 hours. Then, instead of performing a dissolution, you perform a thermalization. So you basically, through the fluid path, you blow helium gas at room temperature. So helium gas has a pretty high heat capacity, so it can heat the sample pretty efficiently. So we lift out the sample cup from liquid helium. We blow helium gas through the sample. You can see here that the sample is heated above the quenching temperature. Then we keep it there for a certain amount of time. All this process takes 10 seconds, and then we plunge it back into liquid helium and inside the NMR coil to assess losses. And if you do that properly, and then here in this, let's say, part of the experiment, you try to switch on the microwaves, the sample is unresponsive. So the polarization is locked. The radicals are not there anymore, so it relaxes slowly, but it cannot polarize either. So a lot of words. I have a video here to show you how the quenching happens. So I just finished to polarize my sample. So this is what we call the quench box, what we use to deliver the helium gas. We connect the fluid path to the quench box. I press the button. I start flushing helium through the fluid path, and then I disconnect it from the quench box and I plunge it back. And this method works efficiently. So we start at 20 millimolar, and after this procedure, the polarization is still there, and we are left with few micromolars, fraction of micromolars of radical. Now the sample is hyperpolarized. The radicals are not there anymore, so we are ready to extract it. But before doing that, we need to pay attention to still to a couple of things. So it's true that the radicals are not there anymore, but the protons in the sample are completely depolarized. So upon extraction, we have to provide enough magnetic field yet to keep the resonance of the carbon separated by the resonance of the protons. Otherwise, the two nuclear pools would exchange energy. That would be relaxation for the carbon. So 50 millimolar is enough. So we equipped our polarizer with a magnetic rail that provides at least 50 millimolar or 50 millitesla, all the way here. Then what we do, we disconnect the loading chamber, very similar to what you have in Kiel, the airlock module. We disconnect it. We have an Albach array here that provides field, and we dock it to this compact transportation device. Is a cryostat. It's a compact cryostat. It's 40 centimeters tall that we developed in-house. Is equipped with an NMR quality Halbach array. Is a permanent magnet of 1 Tesla. The cryostat can stay at 4.2 Kelvin for up to 8 hours. And these are pretty optimal conditions to store these samples. And during this extraction process, let's say heating of the sample, because the extraction is manual, so it takes some time. The whole procedure takes 1 minute to lift it up from the polarizer and disconnect the loading chamber and connect it back to the transportation device. It takes 1 minute, but as far as enough magnetic field is provided, where enough is 50 millitesla, basically the polarization is locked. So we don't lose basically anything in this transfer, although the sample is heating up to 100 Kelvin or so. So the better way to describe this second step is another video. So here is the same sample that I quenched. So now I'm extracting it from the polarizer. I close the gate valve, disconnect the loading chamber. You see this little ring here. This is the magnets around, and I'm putting it inside this transportation device, and I check that this nice hyperpolarized signal is there. So everything went very well in the extraction. And then you just disconnect it from the cryostat. And there is my nice colleague Matilde, who is taking a walk with the transportation device. And we decided to go far. So we put all that in a van, and we drove to Aarhus, from Copenhagen to Aarhus. So 5 hours and 300 kilometers. So let's see now if the trip was worth the gasoline. Well, it depends on what radical precursor you use. So when we started this project, we started with a molecule that is called trimethyl pyruvic acid. That is basically pyruvic acid with 3 metal groups here. That was the one providing the highest polarization. But unfortunately, after the quench, although the radicals are not there anymore, all these metal groups are pretty efficient in relaxing the carbon. So with this precursor here, and at 4 Kelvin and 1 Tesla, the relaxation time is 1 hour, not very long. So then we asked a colleague of us to synthesize deuterated pyruvic acid. So we got rid of the coupling with the protons. With deuterium instead of protons, we increased the T1 to 10 hours. Being the methyl groups the problem, we then moved to another precursor that is alpha-ketoglutaric acid that has no methyl groups, and basically we matched these relaxation properties, again 10-15 hours. And if you then deuterate the matrix, your T1 becomes really long, gets close to 100 hours. So the limitation factor is not the T1 anymore, but how long you can keep helium inside the cryostat. So with this formulation here, we took the trip to Aarhus, we crossed Denmark, we went to our colleague in Aarhus. They're extremely good in application of hyperpolarized C13. And here I'm performing the dissolution from our transportation device. I'm handing the syringe to Magnus to make sure that we have the right volume. And then Lotte is injecting a rat. So at the injection, we had 10% glucose polarization and nothing fancy from the imaging point of view, very standard. And we managed to acquire the first remote dissolution DNP image in a rat. No metabolism, we went really easy, just perfusion, just to see that all that was possible. So that was a little bit far-fetched. We went to Aarhus, was complicated, but this technique can be very useful, for instance, for my colleague Mikko in Kuopio. He has a spinal liner and he has 3 magnets on campus at different sites that are, let's say, 10 minutes walking distance far away. So we implemented the extraction, the quench and the extraction of the sample on the spinal liner, and I built for him an even smaller cryostat because I learned a lot about cryogenics, so I could squeeze down the dimensions. So this is really the size of a PET tracer transporter, and it can hold helium for 2 hours. It is fair enough, and nitrogen for 24 hours. And we, just before UCSF, we performed an experiment just by adding some permanent magnets on the spinal liner probe, but outside. And we added the, let's say, the quench box, so what delivers the helium gas on top of the spinal liner. And the experiment was successful. So very low losses during the quench. And we managed to get also in Kuopio, so outside DTU, because let's say a technique, in my opinion, is robust when it starts working not only in your lab anymore. And we got some percents of polarization on glucose also in Mikko's lab from a spinal line. So that was it from my side. I hope you enjoyed the presentation, and I will be happy to take your questions.
Thank you, Andrea, so much. That was fantastic and very interesting. My list of questions has no end. But first, let's ask the audience. Anyone from the audience would like to ask a question? While we wait for that, Andrea, what about other agents for labile radicals than glucose?
So glucose has no methyl groups. So it has a very long T1. So for the proof of concept, we decided to play safe. So that's the very honest answer. Normal pyruvic acid is a problem because the methyl group turns us crazy when you approach 100 Kelvin. So during the quenching, you lose a lot of polarization, but we have very good results with deuterated pyruvic acid. So carbon-13 label and deuterated. The T1 is 4 hours in this case. So we are running experiments now. I will run experiments next week in Denmark. And we also got from sigma partially deuterated pyruvic acid. So 1 or 2 protons on the methyl group to break the symmetry and basically cut the relaxation from the rotor of the methyl group. And we didn't test it yet. We just got the compound, and I will test it next week. But let's say whatever, all compounds that don't have a methyl group on the molecule, they're extremely easy to quench and transport. Compounds with a methyl group on the molecule, they're a little bit more tricky.
Okay, but you were saying that, so first the complete deuteration helps, but then an asymmetric deuteration helps as well.
Because,
right?
well, with a full deuteration, your methyl group still rotates, but the polar coupling is lower and the relaxation as well. With a partial deuteration, you break the symmetry, and so your rotor
Rotation. Yeah.
doesn't turn anymore. So it's gonna be a crippled methyl
Yeah.
group.
Cool. That's very, very cool and interesting.
So I'll keep you posted. So next, I've been waiting 1 year for this compound. So finally we got it. And on Monday, I will put it for the first time into the polarizer.
Okay. We have a good deuteration group here for chemistry, which maybe we should have talked earlier.
Well, it is horribly expensive and long to get from Sigma. So if there is a talented chemist that can synthesize it for me, I
Yeah.
would be more than happy.
Yeah, I'll ask. That's an entire group on deuteration. All right. Anyone else a question?
Yes, thank you very much, Andrea. I'm super much impressed, especially with
You're
this
welcome.
delivery to Aarhus. Yeah, so I have maybe a stupid question. So you mentioned about this non-persistent radicals that you
Yes.
heat them up and then they are gone. But
Yes.
what is the product? So what is left in the solution from these radicals?
So the leftover products are biocompatible. Now, depending on the molecule you use, the products get different complicated names. I know by heart what you get from the quench of pyruvic acid, because you can use pyruvic acid itself to be the radical precursor and the substrate at the same time. When you quench UV radiated pyruvic acid, you are left with acetic acid and CO2.
Yeah, but the most important that they are biocompatible. So
Yes,
it's okay.
okay. I mean, for sure, from pyruvic acid is biocompatible. Then we didn't run any, for instance, for trimethyl pyruvic acid that looks like the nastiest one because it's not endogenous. Alpha ketoglutaric acid is, for instance. So we didn't run any toxicological exam, but we performed in vitro experiments, and there were no adverse episodes, neither in cells nor in rodents. That's what I can say.
So maybe a stupid question, but just to get things right, if you mix alpha Kg with the pyruvate, right, and you want to polarize the pyruvate, why don't you induce the radical on the pyruvate itself?
You can. That's how everything started.
But you don't want that, right? You want to preserve your pyruvate in that case. How do you prevent it from?
The fraction that turns into radical is very small. So for pyruvic acid, you start at 14 molar and 30, 40 millimolar will become radical. So it's not a problem at all. So the reason to use something else than pyruvic acid, well, first of all, was if I don't want to be bothered by pyruvic acid from the metabolic point of view. So if I want to investigate something else, a different pathway. So if I don't want pyruvic acid on my way, I just choose something that is, for instance, like trimethyl pyruvic acid is not involved in any metabolic pathway. So I can use it as let's say, a biologically silent precursor. And with that one, I can polarize other molecules, acetate, glucose, stuff like this. Of course, if the substrate you're interested in, it is an alpha keto acid as well, then it makes a lot of sense to use it as precursor and substrate at the same time, because it simplifies sample preparations.
Yeah, I can see that.
So for instance, alpha-ketoglutaric acid, we didn't try yet, but alpha-ketoglutaric acid used as precursor and substrate at the same time is a very promising system because there are no methyl groups.
Say it again, alpha-ketoglutarate and what? And pyruvate.
Alpha-ketoglutaric acid on its own. So as radical precursor and substrate. That now UCSF got it clinically approved to study. I mean, there is a peculiar application, but it's to study glioma. But alpha-ketoglutaric acid can be radical precursor and substrate at the same time. As far as you get it, C13 label. Yeah.
The multi-sample that you showed, that wasn't on the spindle liner, right? That was on the Swiss DMP still?
Yes. But,
and do you have a feeling for if it will ever fit on the spindle liner?
It's gonna be one of my tasks.
All right.
But we will go for 2. Because I mean 3 is from the engineering point of view is not super simple, and to be honest, 2 is enough for a decent turnover.
I mean, if you can refill them independently, so audience, right? Take your chance. Otherwise, I'll keep asking my questions. You were saying that the cross polarization is limited by the B1 penetration. What about just designing a relatively long sample? Of course, you may not have the cooling then everywhere.
Yeah, and
also
the microwave delivery can be a little bit problematic.
But from what I understood, like we have a relatively large volume there for the microwave delivery, right? The chamber at the bottom.
Yeah, but let's say I mean I'm not a super expert of cross polarization, but if you were able to use solenoids, it would not have been a problem. The problem is that you cannot use solenoids if you want to do polarization and dissolution, because the B0 is vertical. So you have to use these saddle coils, and with saddle coils a little bit more tricky to get high B.
The strong B1s. We were ordering a dual tune carbon proton wobble box from you, from Polarized, just exactly to test that. But I don't think we have it yet, but we will test it. I mean, we could even think of designing saddle coils with multiple windings, but in the end as well, maybe an amplifier issue.
Well, you will need some. So the spinal liner probe is not locally tuned and matched.
Yeah, exactly. The wobble box. That's what we.
Yes. So you have to get a high B1. If you're not using a solenoid, to get high B1, you are obliged to put capacitors on top of your coil in the cold. Already the length of the transmission line will kill quite a lot your B1. You need local tuning and matching to go very high in B1.
Yeah. I mean, it's convenient to have the box outside.
Yes.
Yeah, for other purposes as well.
We will try to do that, because now the latest update on the small transportation device, I didn't show in this presentation because we're still collecting data, but is now a polarizer itself. So we added microwave capability in the small cryostat. We can polarize protons pretty efficiently to 10%. And the aim is to complete these with cross polarization. And the cryostat is small, and we can use solenoids because the B0 from the permanent magnet is transversal. So we will try the remote tuning and matching for cross polarization in that case.
Yeah, I'm talking to our physics department to rebuild the cryostat that you described, but now that you said you have an upgrade, maybe I'll talk to you again about that later.
Sami is getting one from me.
Okay. Yeah.
And cool. also Christopher Lostensen is interested, because the polarization is fast. It takes 5 seconds. So 1 Tesla for Kelvin, 5 seconds polarized.
Yeah.
Not 70%.
Yeah.
It's around 10% the protons, but in my opinion, yet very interesting.
Yeah. Yeah. Maybe really if you just figure out ways to get it a bit higher, maybe very, very interesting.
Well, you can connect it to a pump, get to Kelvin,
Yeah.
and double the polarization.
Yeah. It's 7 o'clock. If there's no further questions from the audience, I would like to thank Andrea again and everyone else for joining us tonight. It was great to have you, Andrea.
Thank you a lot. My pleasure.
Best wishes and see you again soon.
We talk soon.
Yeah. Bye bye.
Bye,
Thank
bye,
you.
bye.
Bye.
Bye, 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 bye.